Hey guys, welcome back. Today we're going to continue with volumes by revolution, but today when you revolve it, you're going to get a slightly different situation. Let's see if you can figure it out. To get you started, I would like you to graph these two curves, okay? And to do that, you're going to want to first figure out where they are the same, where they are equal. So find where they intersect by setting them equal. Hit pause and do that first and get a decent graph of this. So you set them equal, okay? To get rid of the square root, we can square both sides. We could have also multiplied by 4 on both sides. Doesn't matter which one you do first. If I square both sides, I get x equals, this will be 1/16 now, x squared. Now you can see it's a quadratic. Set it equal to 0. Or multiply by 16 now. Either one, it doesn't matter. So if we multiply by 16, maybe it'll look more familiar to you. Doesn't really matter though. Okay, set it equal to 0. Factor, and we get that x equals 0 and 16, and that should make sense. The square root of 16 is 4, and 1/4 of 16 is also 4. Okay, so now graph these. They both intersect at 0 and at 16. So how neat and clean you do this doesn't really matter right now, as long as you have some idea what they look like. The square root function we know goes like that. This is a line with a slope of 1/4. Okay, so it's going to go something like that. And they cross at, this is 16 comma 4. It's up 4. Okay, so that's the graph that you needed to come up with on your own. So this is the shaded region we're talking about. All right, now we're going to give you a volume problem. We're going to take that shaded region and rotate it around the x-axis. Can you figure out what shape that's going to give you, what that's going to look like? Now, whether you can visualize it or not, I can work you through the math either way. But if we rotate it around here, then the outside shape is sort of like an egg, okay? It's an egg that's solid out here, okay? But the inside has like a cone drilled out of it. So the outside egg cup with a cone kind of out of the middle. So it doesn't really matter whether or not you can visualize these, but what you do need to be able to see, and that's why I asked you guys to watch those videos where they had better graphics than me. What you do need to see is now your circular discs like we had yesterday, now those discs have holes in them, okay? So now if you take out a cross section, it's gonna be a ring or a donut like this. And that's why they call this the washer method. Okay, now when does that happen? When are you going to know to use this method? Anytime your shaded region has space between the shaded region and the axis of rotation. So this white space right here is what's creating a hole in the disc. Okay, so let me clean this up. So what you need to know from here on out, if there is any space between the shaded region and the axis of rotation, so if this shaded region is not completely flush up against the axis of rotation and there's any space whatsoever, all of this, then you have this type of problem called the washer method. Okay, compare that to yesterday. If it was where the shaded region is completely touching the axis of rotation, that would be yesterday's method, the disc method. The difference here is because there is space here, there are holes in our circles. Our circular discs are now washers or donuts. So now you have two R's, the outside radius and the inside radius, and your formula becomes pi times big R squared minus little r squared. Okay, this is the formula you'll use whenever there's any space between the shaded region and the axis of rotation. Okay, so now we're going to take this shaded region here and we're going to rotate it around the x-axis, okay? So my biggest advice is always graph the picture, always graph the problem, always, and always literally draw in what big R and little r are going to be. Big R is going to be the distance from the outermost curve to the axis of rotation. Little r is going to be the distance from the innermost curve to the axis of rotation. And if you look at those two, they are literally, one is bigger than the other, okay? So now let's get this done. My formula will be, the volume will be pi times, we're going to integrate from 0 to 16. And then do this every time as well too. Big R squared minus little r squared, so that you don't mess up, okay? Big R is the distance from the curve to the axis of rotation, so that was the square root of x minus 0, although you don't really need that 0. Little r would be the 1/4 x minus 0. Okay? From here, it's all just algebra and do your integral. So hit pause and finish the math on this. Now, this is often a free response question on the AP exam, and because of the fractions that often arise, lots of times they don't ask you to solve it all the way. Lots of times they just ask you to set up the problem. So if that's the case, you could have left it like this with the squares and not simplify it at all, or you could write it like this. Now, if it's a calculator question, then I would still go this far and then put it in my calculator, okay? If you integrate it by hand, it's not too awful, it's 2 power rules, but then when you have to plug in the 16, it gets a little ugly, okay? So practice both by hand and practice with your calculator. Your final answer for this one should have been 128/3 pi, okay? So even if you use your calculator, only put the integral into the calculator, just bring the pi along. And usually you'll hit math frac to change it back to a fraction if it's a calculator question. Okay, let's try another one from the top. Okay, this time we're going to start with the same 2 curves, but we're going to change the axis of rotation. We're going to revolve around the line y equals -1. So here's y equals -1. Okay, and when we revolve it, the mirror image would be over here. Okay, and it's going to be kind of hard to visualize what this looks like, but the outside shape is still like an egg. Then you have like a funnel, like a megaphone on the inside with an actual opening at the end. Okay, so it's very much like a megaphone. Again, it doesn't really matter whether or not you can visualize what it looks like, because I can work you through the math anyway. Okay, so here we go. Is the shaded region flush up against the axis of rotation? No, it is not. Therefore, this is a problem that has 2 R's. It is your, which is it? Is it the disk method or the washer method? You don't really need to know. This is the washer method. What you really need to know, I don't care if you know the name of it, you have to know that it's 2 R's. There's 2 circles, big R squared minus little r squared, okay? Big R squared minus little r squared. Big R, draw it. Distance from outside curve all the way to axis of rotation. Little r, inside curve to axis of rotation, okay? One of them's literally bigger than the other. All right, what is big R? Subtract the 2 equations from here to here, and that's your big R. So it's the square root of x minus -1, okay? Square root of x minus -1, which of course you'll turn that into a +1. Little r would be from here to here, which is 1/4 x minus -1. 1/4 x minus -1. Now again, if you're just setting this up, you could leave it like that. I just want to remind you that to find a length, it's always top curve minus bottom curve, top to bottom, and you're just subtracting those, okay? Then we're going to integrate still from 0 to 16. That's the setup. You can practice putting it into your calculator if you want to. I'm just going to worry about the setup to try to speed this up. Okay, let's do a different one. Okay, from the top, you got to make sure you get a decent graph. That's very important. So, you know you have a parabola and a line. Okay, positive parabola and a line. Figure out where they intersect. Set them equal and figure that out first. Okay, hopefully you figured out that they intersect at -1 and 3, but we still want to get a pretty decent idea what the graph looks like. Okay, so this is a parabola that's up 1, so it would be this. You should know that pretty clearly. Okay, this is a line that's up 4 and has a slope of 2, but in addition to that, we know that these two are going to intersect at -1 and 3. So it's going to go something like this, right? But more importantly, what we need to know is this point right here is -1, and this point right here has to be 3. So this is the shaded region we're talking about, okay? So let me regraph that and make some space. Okay, so whether or not my picture is great, I can still tell what's going on here, okay? So we're going to rotate it around the x-axis. And again, it's going to give kind of a funnel-like thing, if you care to know what it looks like. The question you need to ask yourself is, is there any space between my shaded region and the axis of rotation? Or is the shaded region completely flush up against that axis or not? And hopefully you can see that there is definitely some white space between the shaded region and my axis. Therefore, this is 2 R's. So we are going to have the washer method. Big R squared minus little r squared. And always write that first. Okay? Now we know our bounds are from -1 to 3. And I just have to find big R and little r. Big R goes from curve to axis of rotation. So that's the line, 2x plus 4 minus 0. If you want to write the 0 or not, doesn't matter. And then it's the parabola, x squared plus 1 minus 0. Okay? So big R is literally bigger. Hopefully you can see that this is bigger than this. And it doesn't matter where you draw it. If I draw big R over here and over here, it's still, big R is going to be bigger. Okay? Just draw them right next to each other. So that's the setup, but you might want to practice again putting it in your calculator and writing it in the correct format. Go ahead and do that now. So if you put it into your calculator, this is the final answer you should have gotten. All right, let me try another one. Hopefully it's starting to make sense. Okay, so this time we're going to throw something else at you. This time we're going to rotate around the y-axis. Okay, well if we rotate it around the y-axis this way, then our picture is going to be over here, and that means our rings are going to be going in this direction. So when we go to add up all of our discs, we have to add up going from bottom up. Okay, so first let me get my picture a little better. Okay, that's what we're looking at. But now our circles are lined up. So that means when we integrate, we're going to be integrating from 0 to 4 on the y-axis. Okay, so what I do whenever it's a y problem, whenever it's rotated around the y-axis, this is going to happen. Whenever it's a y problem, I try to immediately put y bounds from 0 to 4. And I also try to immediately write dy at the end, because what I need to do right now is change all of these equations, or both of these equations, into terms of y. If these are y bounds, they have to be plugged into a y equation. I can't plug x's into y's, or vice versa. So this dy is trying to remind me, this is for me, I'd have to do this. It's going to remind me that I need to change my equations so that they are written in terms of y. So if y equals 2x, that equation would become x is equal to, divide by 2 on both sides, and you get x equals 1/2 y. So that's this equation. This one, take the square root of both sides, and you get x is equal to the square root of y. Okay, so now let's start the problem from scratch. Okay, so is there any space between my shaded region and my axis of rotation? Yes. So we have 2 r's, big R squared minus little r squared. Write it every time. Okay, next, draw in your big R and your little r. Big R goes from the outside curve to the axis of rotation. Little r goes from the inside curve to the axis of rotation. Okay, and now we just got to remember to write them in terms of y, not x. So big R, this guy, is from the parabola, square root of y minus 0 if you want to write it, but you don't have to. And little r is from the line, 1/2 y minus 0. Now when you integrate this, even though it says a y, you still treat it like a normal variable. You put it in your calculator as though it's an x. Just, you got to remember to change your equations in terms of y, but now you integrate like normal. So this one would be an easy one to integrate by hand, so I'd like you to try that. Go ahead, hit pause. Okay, you should have gotten 8 pi over 3 for that one. Okay, we're going to put it all together and try one more problem all the way through. A lot of times they'll give you, hold on a second. A lot of times they'll give you one shaded region, but then ask you to revolve it around a bunch of different things. Okay, this is a pretty common thing. So you got to make sure you get your first graph really good, because you're going to use that same graph for all 3 of these. Okay, so here we go from the top. The square root of x, you should know that graph is this. Y equals 4. Be very careful about those horizontal and vertical lines. That goes through the y-axis at 4. So that's going to go here somehow. That's y equals 4. And x equals 0 is the y-axis. So this is my shaded region. Okay? All right, now I want you to think about what could I revolve this around so that I would use only a 1R. Okay? If the shaded region is completely flush up against it, then it's a 1R problem. Yesterday's method. So if I revolved around this line, it just has 1R. If I revolved around this line, it would also have just 1R because the shaded region is flush up against those lines. But if I revolve around pretty much any other line, then there'll be space and that'll be 2Rs. Okay? So if I go around the x-axis, that means we're going around this guy. Then we're going to need 2Rs. Big R, little r. Okay? Because there's space, the white space. So for that one, my formula would be, we're going to integrate from 0 to I don't know what. I got to figure out what that point is. And it's going to be big R squared minus little r squared. Okay? So what is that point? Well, this is y equals 4, and this is y equals the square root of x. So they're both equal to y, so set them equal to each other. When will the square root of x equal 4? When x is 16. That should make sense that the square root of 16 is 4. So this point right here is 16. All right, now my 2Rs. Big R is 4 minus 0. You got to still subtract equations. So it's 4 minus 0. Yes, I know that that's just 16, but I like to keep it always the same. Subtract the two curves. Okay? The next one is going to be square root of x minus 0. Okay? And you can see this would be an easy one to solve by hand. All right, but I'm just worrying about the setup right now. All right, now let's go around the y-axis. I highly recommend you draw another graph so that you can keep it all straight, okay? It's not that time consuming. Actually, I'm going to do this one first, I think, y equals 6. That's going to be a little easier. Whatever. Doesn't matter. Let's go. Okay, part B, going around the y-axis. So immediately, I think to myself, dy, okay? Next, is there any space between the shaded region and that line? No. So that means I only have 1r squared. Okay? Next, y bounds. This is going from 0 up to 4. Last, this dy, hopefully that's reminding you, change everything to be in terms of y. Okay? So this guy is now going to become square both sides. You get x equals y squared. Okay? Draw in my radius. It goes from here to here. So that's x equals y squared to 0. So it's x equals y squared minus 0. Okay? And that would be another one that's easy to do by hand. Okay, before I do the last one, I want to talk about what order you should subtract your curves. Okay? Like if I wanted the distance between y equals 3 and y equals negative 1, that distance, if this is negative 1 and this is 3, that's a distance of 4. You get that by subtracting top to bottom in that order. Always top to bottom, okay? So even if your graph goes like this, and you maybe are dealing with this shaded region, then you need to subtract top to bottom, 0 minus the equation, okay? Because you need to get a positive length. If it's from right to left, then think about it like this. If this is the line x equals 1, and then this is the line x equals 5, you have to now subtract from right to left to get a positive length. So it's right to left for these problems and it's top to bottom. Okay, so now let's do the last one. Okay, we have the same shaded region. This is y equals 4. But now we're going to rotate it around a line, y equals 6. Okay? So that's y equals 6. So we're rotating around this line. All right, so is there any space between my shaded region and the axis of rotation? Yes. So that tells me I have to use 2Rs. Big R squared minus little r squared. Next, a line that is in the same direction as the x-axis is going to be treated like an x problem. So we have a dx at the end, okay? Same as rotating around the x-axis. So we're going to have x bounds. That means it's going to go from 0 to 16 again. Now big R and little r. Big R goes from the outside curve away from the axis of rotation. Little r is from the inside curve to the axis of rotation. Okay, subtract big R, top minus bottom though, 6 minus whatever that curve was. Okay, so it's 6 minus the square root. The other one is 6 minus, what are the two curves you're touching from here to here? 6 minus 4. Okay, I haven't been doing the integration because this is getting to be a very long video. I just wanted to set them up a bunch of times. So hopefully that works for you. I know it's not the easiest thing for me to teach online. I hope you're doing okay. Good luck with your homework. Since I want to make sure you really get it before I assign a whole bunch of problems, I'm going to change the assignment to be just 9, 12, and 15. Just those 3 problems. If you feel like you understand it, then keep going all the way to 18. But I only want you to necessarily do 9, 12, and 15 so that I can make sure you do a really good, wholehearted attempt at those before we keep going. We'll be working on this further tomorrow. Okay? Good luck, guys. Bye.